We're going to learn work and energy today. First, let's start with the most common form of energy, kinetic energy. Basically, anything that is moving has kinetic energy. Kinetic energy, sometimes we write it as Ke, sometimes we just use E to denote it. It can be calculated as 1/2 m, which is mass, v, speed squared. And now if you have more than one object and they are moving, the kinetic energy of those two objects, the system of two objects, is kinetic energy of m1 plus kinetic energy of m2. So this is kinetic energy of m1, 1/2 m1 v1 squared. This is kinetic energy of m2, 1/2 m2 v2 squared. Now, because it's 1/2 mv squared, and for m, its unit is kilogram, and for speed, its unit is meter per second, so speed square is meter square per second square. So the unit for energy is kilogram meter square per second square in SI unit. Now, because this is too messy, so we define another unit which is equals to 1 kilogram meter square per second, so we call it joules. So 1 joule equals to unit for energy in SI unit. 1 joule is 1 kilogram meter square per second square. Now, kinetic energy does not depend on the direction of the motion. It doesn't matter this object is moving to the right or to the up. As long as its mass is m, its speed is v, it doesn't matter which direction it's moving, so even the velocity is not the same. As long as the speed are the same, they have the same kinetic energy. It's 1/2 mv squared, and v is speed. Now, if you look at it one more time, K equals 1/2 mv squared, and you see if you double the mass, your kinetic energy would double. If you double the mass, the kinetic energy would double. Okay, if you double the speed, what's going to happen? If you double the speed, you'll find out your kinetic energy. If you double the speed, 1/2 m2v squared, it's not going to double, but quadruple, 4 times. If you double the speed, your kinetic energy would be quadruple. Okay, this is kinetic energy. Let's talk about work. Let's look at this scenario. You have a hockey player use a pad to pad a puck. Okay, he applies some force from here, move the puck to here. Now here the velocity of the puck is 0, and it has some velocity here. Vf is not 0, which means the kinetic energy of the puck increased. Now where is this kinetic energy coming from? It's from the energy of the player. So the player transfers some of his energy, which is bioenergy, to the puck through the force he applied through the puck. Anyway, see, kinetic energy is 1/2 mv squared. This is energy of one object. Work is energy transferred from one object to another object. So work has to have at least two objects involved. So work is energy transferred from one object to another object through force. So the player applied force on the puck. So he did some work on the puck, and the puck moved. And how are we going to calculate the energy transferred and the work? So we're going to use my favorite kinematic equation, if you still remember what's that. My favorite kinematic equation, 2 times acceleration times displacement equals final velocity square subtract initial velocity square. Now, we have Newton's second law, acceleration equals force over m. So let's make a very neat assumption. Let's assume the force applied by the part on the puck is a constant. So the acceleration of this puck from here to here is constant. Apparently the force from here to here is constant as well. So we have this constant acceleration equals this constant force. Constant acceleration equals constant force of m. Now, my favorite kinematic equation gives us this. And now you can just move this 2 and m. This 2 and m from left hand side to right hand side, you have this equation. So basically what you need to do, you multiply m on both sides, you divide the 2 on both sides, you get this equation. Okay, so, and now we can observe we have 1/2 mv squared, 1/2 vf squared subtract 1/2 mvi squared. So what is 1/2 mvf squared? So this is KEF. This is KEI. So we have its final kinetic energy subtract the initial kinetic energy, which is the change of kinetic energy. Now this F times displacement, force times displacement, we call it work done by the force. So the work done by the force can be calculated using the force and the displacement. Now this is a special scenario. The force is the same in the same direction of the displacement. And of course, we assume there's no friction in this problem, in this case. So force times displacement give us work. Now, let's look at another scenario. Now you have a puck going this way and the coach catch it. So her part is initially here, he apply force until the part gradually move here. So you see the force is pointing to the left. The puck is moving to the right. So you see the force and the displacement is in opposite direction. What does it mean? How about the change of kinetic energy of this puck? So you will have the initial kinetic energy is not zero, but kinetic energy, final kinetic energy is zero. So which means if you have KEF subtract KKI, KI is not zero, KF is zero, so you will have that K is smaller than zero. So in this case, which means she's doing negative work. If you go back to this one, you see force is in the same direction of displacement, is doing positive work. That this one she's doing negative work because the force is in the opposite direction of displacement. So work can be positive, negative, or zero, but it's always a scalar. So how are we going to calculate work done by a constant force in general? So it's always, if you have your force and then you have your displacement, there would be an angle between them. So the work is force times displacement. You can call it delta I or you can call it delta x. So in order you're not confusing, let's change it to f delta x. F delta x cosine theta, and the theta is angle between force and displacement. So apparently, which means if this angle is somewhere between, if theta is 0, 90, you have positive work. if theta is exactly 90, cosine 90 degree give you 0. So there's no work. If theta is somewhere between 90 and 180, negative work. So this, what kind of work the force is going to do is entirely depends on the angle between the force and displacement. So look at this example. So somebody is pulling a sleigh with force F, and there is normal force, gravity, this pulling force, and displacement is to the right. So you see, normal force, does normal force doing work in this case? So you need to find what's the angle between normal force and the displacement. So what I find is 90 degree. Normal force, the angle between normal force and displacement. So normal force doesn't work. The work is 0 joules for normal force. How about this force? So this angle is somewhere between 0 and 90 degrees. So it's going to do positive work, but you have to use this cosine theta. So the work done by this force is F that x cosine theta. And you can also do a decomposition. This is F cosine theta. Only this component, the x component of F doing work. The y component of F, which is F sin theta, it doesn't do work because F sin theta is perpendicular to the displacement. Now let's check this example. You have 3 scenarios of force and displacement. Case A, is it going to do positive work or negative work? Write down your answer. Case B, force pointing down, displacement pointing down, is it positive or negative? Write down your answer. Case 3, F pointing down, R pointing to this direction, positive or negative? So write down your answer. Okay, now I will give you the answer. Case A, F pointing down, R pointing up. What's theta? Theta 180 degree. What is cosine 180 degree? -1. So this one is negative work. And this one, F pointing down, displacement pointing down, so theta should be 0. Cosine 0 give you 1, positive. This one, theta is somewhere between 90 degree and 180 degree. Cosine, this angle should also give you negative answer, is negative. Okay. So this is the first part of our energy lecture. Let's stop here and I will record another lecture of energy and work.